Welcome to our podcast on industrial robotics applications and warehousing and distribution. I'm Eugene Demetri, Editorial Director of Robotics 24/7. Joining me today are Nick Longworth, Senior Systems Application Engineer, and Bruce Muir, Director of Distribution Automation at SICK. Welcome, gentlemen. Can you talk a little bit about what each of you does at SICK? Why don't we start with you, Bruce?
All right, thanks. Appreciate it, Eugene. My name is Bruce Muir. I come to you with 32 years of experience in the material handling industry. Joined right out of college from NC State. I've worked at major automation integrators throughout my career. I've been self-employed several times, been in the airport industry, and I served in the retail industry as a capital equipment deployment manager. Most recently, I've been with SICK for about 8 years now. I'm a sales leader. I run sales teams that call on automation integrators in the logistics environment, as well as all the retailers and airports in the country.
Right. And Nick?
Yeah, so I'm Nick Longworth. I am a senior application engineer with SICK. I've been with SICK for about 4 years, focused mainly on our industrial robotics technologies, whether it's robot guidance. We can get into a little bit of safety. We can talk about a lot of our other sensor technology and how it relates to industrial robots. Prior to SICK, I was an end user for about 10 years. I designed, built, and maintained anything from a welding, assembly machine tending, distribution, depalletization, really any type of robotic system. So a lot of experience with these types of applications and kind of what we'll be talking about today.
Right. And let's get into our conversation here. I know we're talking about industrial robots and warehouses, and most people, when they hear robots and warehouses, are thinking of autonomous mobile robots or AMRs or automated guided vehicles, AGVs, but we're really talking about industrial. Can you clarify or explain what you mean by that?
Sure, I'll get started. I think it's what you say is very common in the industry. I think when people talk about robotics in the logistics field now, your mind immediately goes to autonomous mobile robots, essentially smart AGVs that are being used to deploy all over warehousing industries right now. I think more than 1 billion lines of picking has been supported now by autonomous mobile robotics, kind of taking that space where the large pick module used to sit in warehousing environments. And I think, that's more making people more efficient in automating the non-value added process of walking and things like that in the warehousing environment. That's not what we're talking about in this particular case, though that's a great field of study and conversation to have. We're talking here more industrial robotics that would actually take the place of people, palletizing, picking, things like that. Nick has a lot more information about that sort of thing.
Yeah, and how I typically differentiate between different types of robots is the kinematic model. And when I say kinematic, it has to do with how the robot measures its position in space, and how it understands, say, from my 0 point here and whatever I'm doing up here, how do I calculate where that is relative to that? And different types of robots have different mathematics, and they're drastically different mathematics in terms of how they're going to track themselves. So typically when you start looking at those calculations, there becomes a very clear differentiator when it comes to technology that can integrate with those robots based on those kinematic equations. So when you look at those equations, articulated arm, something like a FANUC or a KUKA or something like that you would see, that's an actual arm that's going to move around and do pick and place or welding or something like that. That's one type of robot, and it's called articulated. You might see another type would be AGVs, like you've mentioned, drones, legged. Those are all drastically different models in terms of how they work. So what we'll be talking about today is more articulated, maybe a little bit of gantry, but mostly articulated robots we'd probably be getting into.
Yeah, and there's Delta and Scara robots and all other kinds of interesting systems that people are right now thinking a lot about humanoids, but there's plenty of other types of robots that are doing real work right now.
Yeah.
Speaking of that, can you guys give some examples of some common applications that industrial robots are doing in warehousing and logistics? You mentioned taking place operations and palletizing, but can you go a little bit more into that? Bruce?
Certainly. So I think when we walk through the warehousing environment, we look for collections of people that are doing work, and then identify any repetitive or potentially ergonomically unfriendly tasks that could be performed by a fixed robot. I think we did talk about AMRs, and people are mounting robotic arms to AMRs today, and trying to figure out that process of picking on top of where the AMR would actually go to the storage location and pick product off the shelf. Likewise, we can have totes of product move underneath into a picking area where a fixed robotic arm does picking out of a tote. But I think the biggest places that we see the opportunities for ergonomics, as well as offsetting collections of large pools of labor, are, I think truck loading and unloading is a big thing right now, especially when we move to a more aggressive OSHA stance on what's acceptable or not based upon lifting standards, and how to keep people safe, as well as just the difficulty of finding people to do that kind of work, and the more than 100% turnover that exists in those sorts of tasks. When there is sortation, especially item sortation in a distribution operation, things like tilt tray sorters or Bombay sorters or cross belt sorters, there is the loading of those sorters that is a very labor intensive process. Whether an AMR or a conveyor system delivers a full tote full of a bunch of mixed product, and a robot has a task of removing each of those items and putting them onto the sorter, or whether it brings in that same infrastructure may bring in a tote of all the same items in there, say t-shirts in a bag or something like that, and we have to pick a finite number out of the tote and return the unused quantity back to the storage feature. That's another good use case. Palletizing and depalletizing is a fantastic one. When we look at the inbound automation and outbound automation in the distribution center, and that has both labor intensity and ergonomics involved, and we're seeing more and more applications of belt picking as well. Things where, especially in the courier, express, and parcel industry, I know all of the major players in that industry are rushing to find fixed robotic solutions to pick and sort.
Yeah, and I think a lot of what you're discussing there really boils down to a couple of factors. One is ergonomics. Do you have good or bad ergonomics in the application? And that's a common theme throughout a lot of different industries, not just logistics and warehousing. Is using a robot because these things are big, heavy, and they could hurt people. So that's a common thing. Throughput is another big piece. Is, can you get people? Can the people actually do this fast enough for what you're doing, or will a robot be a better option? And really the opening here is the technology. What technology are we able to apply, and is it able to make that robot flexible enough to do these applications? Because unlike something like in a factory where you're doing the same thing day in and day out, you need a much more flexibility in a warehouse in terms of what you're going to see and the type of things that you have to pick. So I think a lot of what Bruce just mentioned does go back to those two factors of ergonomics and throughput. I'm not sure if you would add any others to that, Bruce.
It would just occur to me when you talked about flexibility. I can't think of a much more requirement of flexibility than unloading and loading of trucks. I think most of the major integrators or manufacturing of traditional logistics operations have had varying different types of designs of equipment to load and unload. And I think there's some really great ideas, especially as it relates to the mechanical idea of getting in and out of trucks and what kind of conveyance might be attached to that. But what we get involved with and what Nick's biggest expertise is in the perception of what the robot sees when it looks at that wall of boxes and decide what to pick and what to grasp and how to grasp it. To me, that's one of the most fascinating developments that we've had so far, especially as it relates to flexibility. Think about that, Nick.
Yeah, I think that really it's a good point because it's what has really opened up these applications. You didn't see a lot of robots other than AMRs in warehouses for a very long period of time because you have so much variation in what you're trying to pick or interact with. It's not something, again, where you're dealing with this single widget day in and day out, and all you have to do is pick that widget. If you were to try and do it the ways that you see in automotive or the way you see in metal and machinery, you're going to have a very high fixed cost in order to work with anything. So those ways of perceiving items and being able to guide the robot to go pick those items, those are newer, and those have really enabled these applications to be able to be solved because now we can, a poly bag, a clear poly bag with a shirt in it comes down the conveyor. We need to pick that. Well, the next thing's a box. And the next thing after that is who knows what. It could be a mailer or a bag, another bag or anything like that. And we have to be able to image and recognize and guide to all of these things within pretty much just like that. It cannot be slow. It needs to be dynamic, and you got to be able to do it. So there's a lot that has gone into it from a technology standpoint that has really enabled these applications now in that regard.
Just going to say, what types of technologies, Nick? Like, I think about the applications I've brought to you to solve in the past. Things like shirts in a clear bag, where typical vision, two-dimensional vision, might not be able to solve that. What other types of technologies are you able to bring to bear to solve applications?
You're dealing with again, traditional 2D vision, not going to do something like that, because traditional 2D vision, you're dealing with trying to generate contrast and then using a shape matcher. And so again, going back to a bag, you're talking about a flexible item that can look like any shape. It doesn't really matter. Pick a shape, it looks like a cloud. So it's something where deep learning has come in and hasn't really enabled us to do segmentation that way, where it really understands, similar to our eyes, what is what. But in addition to that, you've got into 3D vision, where you have some higher speed 3D cameras now that can give us, in combination with that deep learning, we can all of a sudden, create a point cloud that now we can get full 3D positioning, and the robot can just go snatch this thing from wherever we want. It's not nearly as limited as it used to be in the past. And again, that's what's really opened up things like depalletizing, truck loading, unloading, induction, which is basically you can almost look at induction as a bin picking operation in a lot of cases. Those kind of things are now opened up because you have that technology available and in a state where it's capable of this type of application.
One more thing here, Eugene, that I'm pretty fascinated by, and that is, so far we've talked a lot about the picking of product. So we pick product out of a tote, we set it on a conveyor. We pick product off of a belt, we set it on a conveyor. We pick product out of a truck and we put it on a conveyor, and we pick product off of a pallet and do something with it. The palletizing, mixed case palletizing, and mixed case truck loading, I think is pretty fascinating too, because of course what Nick is saying, we can certainly perceive all of those things, but what about the calculation and like the things that people are really good at doing is figuring out how a field of boxes in front of me fits well and organized on a pallet and maybe in a truck. How do we is it deep learning or AI or something like that helps us solve those applications where we actually have to put the puzzle pieces together?
So that's something that more just requires prior knowledge. So I don't know if I'd say deep learning is always necessary in those, maybe in some cases, but there are a lot of rule-based systems already out there from different robot manufacturers to do that Tetrising work. And the main thing is they have to know what's coming down the line. And so you got, we have other technologies on those conveyors. You mentioned those conveyors that are tracking what is there and what's coming down to that robot, and knowing what's coming. The robot can do a lot of calculations in terms of how that best fits up to maximize space. Lots of things like that in terms of a dynamic palletizing, a dynamic loading, that kind of stuff that it's been available actually for a while. But again, the opening here has been really the ability to start implementing these in warehousing environments with good ROI and that kind of stuff, to have those technologies that are enabling that side of the process to make it worthwhile.
Those are all excellent points. And Nick, you've been talking about, obviously the technologies to recognize and ultimately to enable the robots to manipulate the items. But can you talk for a moment about how the distribution center environment has maybe different perception constraints and requirements than, say, a factory environment, right? Where, you may still need perception to handle items coming down the line, but I think you were alluding to a certain amount of predictability versus variability. Can you talk about just the constraints or things that are different in this warehouse and distribution space that we are now applying these industrial robots and sensing systems to?
Yeah, and so you're exactly right. In a factory, let's say you're working on a laser cutter, you're working on a CNC machine or an assembly line. The thing that the robot is doing is the same day in and day out, or maybe changes, slightly. Maybe you start making a different part, but it's a similar line of part, maybe just a different size or a different thread or something like that. But the tooling that robot has and the fixturing that you can put the parts in, that can all remain the same. That makes the automation process not need perception. It doesn't need to have a vision system to tell it where things are, because they can be fixtured up and held in a known location, and an operator just throws them in there and throws, I don't know, a couple hundred on a rack, and while the robot goes and runs the rest of the day. Things like that are capable in a factory, because you are doing the same thing day in and day out, and it's, I wouldn't say it's cheap, but it's cost effective is probably the way to put that. You're able to do that kind of thing versus those traditional methods that you see in factories with high repeatability. They have low mix, high volume. That's kind of the term here. We're going low mix, high volume. Those techniques of using fixtures and stuff like that, it would not be cost effective in a warehouse where you have, 10 things on a conveyor and they're radically different things. And you wouldn't be able to use the same shape matcher or the same fixture or anything like that to be able to figure out where these are for the robot to go pick them. And the other thing I do always mention here when it comes to vision is the robot's not, the camera is not the only piece of this, the perception. It's the other piece is the robot program and the tool. The tool has to be able to pick what you're trying to see. And that's another big piece of these sort of things becoming an application in the warehouse, is having some investment into different types of soft tools that are able to kind of form to what you're picking, rather than having a rigid tool, which a robot is typically a very rigid machine. It's a bunch of metal and motors. And same with the tools. They are traditionally pneumatic based, or there's some electric ones, but they typically don't have a whole lot of give. They like to go here and here. So a lot of technology that's come out from a picking standpoint is now more flexible, where you can kind of see it grab around things, or maybe the suction cups have advanced to a state where you don't necessarily have to have something on every suction cup in order to create suction. Things like that have also enabled this this field in the warehouse, because you got to be able to pick what you see as well.
And to follow up on that, what sorts of enabling technologies, you mentioned obviously some of the improvements in grasping, but even in perception and then the vision processing like GPUs, what kind of enabling technologies are you seeing that are evolving or developing to aid industrial robots in these environments?
Yeah, so with 3D vision, you've had 3D vision for years. It's something that, you can create a point cloud, and I I know of point cloud based systems from the early 2000s. But the issue is, how do you process that point cloud? I think that's where you're going is, what has changed in the past 5 years, let's say, that has made this something that we can now do that we couldn't do before. And generally what's changed is the ability to process, and process quickly. And the biggest adder to that has been GPU acceleration, so graphics processing units. And that's a lot of times what your computer is using to do rendering or doing your displays. But essentially what it is there's a computer chip in there with a ton of cores. It has a ton of little brains, essentially little decision makers. And when I say a ton, you're talking about thousands. And the PCs can now leverage those. It can take a deep learning process or a point cloud generation process, and it can place it into that GPU with all those little decision makers and have that done very quickly. Versus in the past, you were relying on a standard CPU in a PC, which only has, normally 8, maybe 12 decision makers. They're very fast decision makers, but you only have so many. When you can do a parallel process like point clouds or deep learning, having a lot more decision makers really makes it a lot faster. So that GPU has been a huge addition to this type of technology. It's worth noting some history that deep learning, the idea of it has been around since the 1940s. Perceptron was a textbook method of deep learning in the 1940s. It's just every time you see deep learning come up throughout history, what happened was it never made it to mainstream because there was never the technology to really bring it in and be useful until maybe 80s, 90s, where you see the airlines starting to mess with our pricing based on our buying habits and stuff like that. That was a deep learning algorithm. But then, in production, you need a much higher processing level than, say, an algorithm that tells you how to price a ticket for an airline. And so it took until now to really get that GPU acceleration, and something that we can really use in the field and have strong results for an application because of it. Bruce, I don't know if you see anything else. I know that was a bit of a tangent on technology there.
No, I think it's important. The cost models associated with distribution. I've been in this industry for a long time, and for the first, 25 years of my career, we were trying to offset, relatively inexpensive labor in warehousing, and that's kind of where real automation always got stuck. We were doing mechanization, we weren't doing automation. We were putting conveyors in to eliminate walking in order to make people more efficient. Now we're talking about actually replacing people from time to time with robots. And the big thing that makes that happen now are the cost models associated with it. The inflation is driving wages, but also I think, what do they call it? The great layoff, or the
Great resignation.
We've seen great resignation. Sorry, we've seen so many people leave the warehousing pool of potential labor that now, instead of just offsetting labor, now we're looking at retailers out there that just can't fill their warehouses with people to do things, and that drives a completely different cost model than having to hire too many people. So that's where how the industry is driving to automation over what we just considered mechanization in the past.
Yeah, and that's definitely you put those two pieces together, and that's why you're seeing adoption all of a sudden. And one of the things I think it's worth mentioning again, because you made that comparison, Eugene, to factory automation and where robots are currently highly adopted. We sell 40,000 new robots in the US per year. It's not like we are just getting into articulated arms and traditional robotics, or industrial robotics. The first one was installed in 1961. So it's been a long time, and there's been a lot of adoption in this industry, but why has it not ended up in warehouses? So that technology piece I mentioned as a part of it, but also what Bruce mentioned about, the cost models associated with how do you replace somebody is a big piece as well. And you go back to, again, a factory, you pay people, on a job, you're $24-30 an hour versus a warehouse is what, 14-15, Bruce, something like that.
Probably
And
about
so,
right.
yeah, so the ROI that you look at, that return on investment in a warehouse has always been significantly lower. You're talking about half the wage versus, any other benefits where you see, a union in a factory getting probably higher end benefits, and you get lower benefits in a warehouse, that kind of stuff. All that factors into ROI and really affects that cost model that you might see in a warehouse, where it might not make sense to implement a robot over a human, especially when they're not flexible enough to really do the job effectively before some of this newer technology.
And then speaking of the, financing models, Bruce, there's new approaches to trying to make industrial automation more accessible, right? Including robotics as a service. And can you talk for a moment to that in terms of helping to make automation of all kinds, but in this case, industrial automation, more accessible?
That's a great topic, especially as it relates to the seasonal nature of a lot of the warehousing and distribution that we see here. The peak to average ratios of distribution can be substantial, especially in the retail space. So when you create an automation environment, you're effectively creating a funnel. That robot can only grasp so many pieces. That conveyor can only go so fast. So you create a nice base layer for how to get work done. But what do you do to add additional productivity required at the times that productivity is most needed, when those retailers need to get the product on their shelves for Black Friday through the season? And I think that what we're seeing now is things like collaborative robots. Of course, you mentioned robots as a service, and that's a very important model that's being brought in. Being able to use operational expense versus capital expense in order to leverage automation. So there's new cost models like that, new finance models, I guess you'd say. But we're seeing things like just the increased throughput available with robotics, and as the control systems and the sensor systems, as they get more powerful and more affordable, we can do different things with the robots. And then of course, we haven't talked about collaborative robots at all. The robots that aren't collaborative, that have to work in a safe space where people can't be near them. That's one of the things that we do as a company more than anything. And the thing we're known for the most is safety. And but not only is safety keeping people away from robots, but we have different types of robots now that can actually collaborate with humans. So if that robot is sitting there picking product and throwing it into a tote, there's certain circumstances where I might be able to step in beside that robot and work alongside it in order to make it more efficient and me more efficient. So there's several different emerging applications like that we can use in order to make sure those peak volumes are met.
Yeah, and it's important. I think you touched on this briefly, the robots as a service, and that model allows you to lease robots essentially, and that's full robot systems where you might be able to just roll them in to a specific application and just plop it down and off it goes, kind of thing. And it's important to mention a big difference between a traditional robot arm and a cobot arm. Not in addition to safety, is actually weight. A cobot arm is lightweight, and when I say that, I literally can take the biggest cobot arm I know and throw it on my shoulder and walk out the door. It's not a heavy robot whatsoever, which allows you to do things like just let's move it over here, let's move it over there, let's bring it on a truck over here, and let's put it in this facility, versus a traditional robot. Well, those things could weigh hundreds of pounds, and they require a significant amount of energy, possibly at higher voltages, stuff like that. Not all of them require that, but the smaller ones, say, might be able to handle some lower requirements, but the smaller ones also might not be able to do what you're trying to do, whereas a cobot has the reach. So it is important to recognize that cobots, in addition to that safety piece, have also introduced a lightweight model, which is now able to do things like system as a service. So,
Bruce and Nick, this has been a really great conversation, and I appreciate your time. And I'd like to thank SICK again for sponsoring this podcast. And I look forward to continuing this conversation again. Thank you, guys.
Yeah, great conversation. Thanks a lot for the
Thank you.
opportunity, Eugene.